Great. So we will continue from where we left off, as I promised. Right. So we were looking at linear regression, and we looked at subset selection, and then we looked at shrinkage methods, and then finally we came to derived directions. Right. I said there are 3 classes of methods. Right. So we are looking at a couple of examples of each of those classes of methods. The first one we looked at was subset selection. So we looked at forward, backward selection, and stage wise selection, stepwise selection, and all that. And then we looked at shrinkage methods, where we looked at ridge regression and lasso. And then we started looking at derived directions, right, where we looked at principal component regression. I said the next one we will look at is partial least squares, and I gave you the motivation for looking at partial least squares. It is mainly because principal component regression only looks at the input data, okay, does not pay attention to the output, right, and therefore you might sometimes come up with really counterintuitive directions. Like in the example I showed you with the plus and minus 1 outputs. Okay. So the basic idea here is that we are going to use the y also, right. Just like the usual case, I am going to assume that y is centered, right, and I am also going to assume that the inputs are standardized. Okay, this is something which you have to do for both PCA and partial least squares. Essentially you assume that the each column, right, is going to have 0 mean unit variance, right, on the data that is given to you, you make it 0 mean unit variance, so that you are not having any magnitude related effects on the output. Okay. So what I am going to do is the following. If you remember how we did orthogonalization earlier, something very similar. So I am going to look at right. So I am going to look at the projection of y on xj, right. Then I am going to create a derived direction which essentially sums up all of these projections, right, I have computed. Basically I am computing the projection of y on xj, right. So this is essentially the direction, is the vectorized version of it, right. I am going to sum all of this up. So essentially what I am doing here is I am looking at each variable in turn. I take each xj in turn, okay, I am seeing what is the effect on y, right. So how much of y I am able to explain just by taking xj alone, right, and I am using all of that, I am combining that and making that as my single direction. So individually taking each one of this all by itself, okay, individually taking each direction by itself, how much of y can I explain, okay, and that becomes my first derived direction, that is my z1. Okay. So that is the coefficient for z1 in my regression fit, eventual regression fit, okay, that is a coefficient for z1. You can see what it is, right. So I have taken y and regressed it on z1, and that essentially gives me what, the coefficient for z1, right. So how do I go on to find, okay. So I am looking at how much of y is along each direction xj, right. So in some sense you can think of it as, if I have one variable xj, right, how much of y can I explain with that one variable xj, okay. So I am looking at that, and then my first direction z1 is essentially summing that univariate contributions over all my input directions, right. Suppose I have 2 input directions, Fortunately I have to do this in 3D. Suppose I have two input directions. So what I am going to do is I am going to take my y, right. So project it on x1 alone first, right. Project it on x1 alone and on x2 alone, right. Let me redo that, make it easier. It's a little tricky to do this in 3D, but anyway. Right. No, it's going to be hard to do it on the board pictorially for you. Okay, I am not going to do that. No, I really need to get a. I actually have to plot a function y, right. I can't just do it with single data points y. That doesn't make sense. So I actually have to get you a surface y on x1, x2, and then talk about the projection. So that's going to be hard, right. But the basic idea is I take y, right. I find the projection of y along x1. Okay. Then I find the projection of y along x2. Okay. Now I am going to take the sum of these two. Okay, and whatever is the resulting direction, that I am going to use that as my first direction. Okay.
How is it different from PCR? In PCR we are projecting on each of the eigenvectors.
Yeah, so in PCR what we did was we first found directions in x which had the highest variance. Here we are not finding directions in x with the highest variance, but we are finding directions in x, right, some sense components of x which are more in the direction of the output variable y, right. So eventually you can show that, which we are not going to do, but you can show that the directions you pick, the z1, z2, z3 that you pick are those which have high variance in the input space but also have a high correlation with y, right. So it is actually an objective function which tries to balance correlation with y and variance in the input space, while PCA does only variance, PCR does only variance in the input space, does not worry about the correlation, but partial least squares you can show that it actually worries about the correlation as well, right. So you find the first coordinate. Now what you do, you orthogonalize So what should I do now? I should regress x1. So what should I be doing now? I should regress x1 like xj on z1, right. This is how we did the orthogonalization earlier, right. So you find one direction, okay, then you regress everything else on that direction, then subtract from it, that gives you the orthogonal direction, right. So essentially that is what you are doing here. The expressions look big, but right, the expressions look big, but then if you have been following the material from the previous classes, then it is essentially we are just reusing the univariate regression construction we had earlier, right. So now I have a new set of directions which I call xj2, right. xj1 was the original xj's I start off with, right. Now I have a new set of directions which we will call xj2, and then I can keep repeating the whole process, right. I can take y, project it along xj2, right, and then combine that and get z2, and then regress y on z2 to get theta 2, right. So I can keep doing this until I get as many directions as I want, right. So what is the nice thing about the Z1, Z2 and other things? They themselves will be orthogonal because they are being constructed by individual vectors which are orthogonal with respect to the all the previous z's that we have, right. Each one will be orthogonal and therefore I can essentially do univariate regression. So I do not have to worry about accommodating the previous variables. So when I want to fit a zk, I can just do a univariate regression of y on zk and I will get the coordinates theta k, okay. Is that fine? Great. So once I get this theta 1 to theta k, how do I use it for prediction? Can I just do like x beta, like I do x beta, can I do x theta? Huh? Can I? No. What should I do? Well, I can do xz. I mean, I'm sorry, theta z, right? I can do theta z and predict it, but then I do not really want to construct this z directions for every vector that I am going to get. So I do not want to project it along those z directions. So instead of that, what I can do, if you think about it, each of those z's is actually composed of the original variables x, right. So I can compute the thetas and then I can just go back and derive coefficients for the x's directly, because all of these are linear computations. All I need to do is essentially figure out how I am going to stack all the thetas so that I can derive the coefficients for the x's, okay. Think about it, okay. You can do it as a short exercise, but I can eventually come up and write right. So where I can derive these coefficients beta hat from these thetas, right. So I will derive theta 1, theta 2, theta 3, so on and so forth. I can just go back and do this computation. So you will have to think about it, very easy, you can work it out and figure out what the number should be, right. And what is the m doing there? The number of directions I actually derived, right. So number of directions I derived from the PLS, right. So here I have the first direction, I can keep going. Suppose I derive p directions. What can you tell me about the fit for the data? If I get p PLS directions, it essentially means that I will get as good a fit as the original least squares fit, right. So I essentially get the same fit as the least squares fit, okay. So anything lesser than that is going to give me something different from the least squares fit, okay. Here is a thought question: if my x were originally orthogonal to begin with, my x were actually orthogonal to begin with, okay, what will happen with PLS? Huh?
Z's will be the same as x.
Sorry?
Our z's will be the same as our x's. Z will be the same as our x.
Z will be the same as our x's, right. And what will happen to Z2? Can I do the Z2? No, right. PLS will stop after one step because there will be no residuals after that, right. So I will essentially get my least squares fit in the first attempt itself, okay. So that is essentially what will happen, right. So we will stop with regression methods